This is a presentation on parallel prefetching in Monte Carlo simulations created for the 21st Symposium on Thermophysical Properties. My name is Harold Wiggs-Hatch, and I am a permanent staff member in the Chemical Informatics Group of the Material Measurement Laboratory of NIST. So why are parallel algorithms important? Well, it's because while the number of transistors and microprocessors continues to increase over the years, the clock speed and single-thread performance hit a plateau around the year 2005. Processors aren't getting much faster anymore, they simply have more cores. And this means that a single serial simulation that took a month in 2005 still almost takes a month in 2021, unless it is parallelized to take advantage of multiple cores. What are parallel algorithms for Monte Carlo? Well, before describing parallelization with prefetching, I want to briefly overview some other parallel algorithms in order to discuss their advantages and disadvantages and see where prefetching fits in. So domain decomposition is one example, and is where you decompose your domain into cells that are able to separate processors to compute trials simultaneously. So in this example, an active cell is shaded, and only one particle per active cell is perturbed. But the move is rejected if the particle goes outside of the active cell. As you can see, this domain decomposition approach is most efficient when particles interact over short distances compared to the entire domain. And domain decomposition is more efficient for whole system updates like molecular dynamics algorithms, such that many particles can move at the same time, as opposed to Monte Carlo with traditional single particle perturbations. Configurational bias is also a parallelizable Monte Carlo algorithm, and in this serial example, multiple positions are tested for each bead in sequence to grow a second isobutane molecule. This can be parallelized by attempting the multiple independent placements of each bead simultaneously. However, improvements such as dual-cut configurational bias that is much more efficient than configurational bias also unfortunately decreases the parallel efficiency. That's because the time spent on the multiple simultaneous trial positions of each bead is reduced with a smaller cutoff, while the full expensive potential is used after the molecule is grown during an inherently serial step. Flat-Histogram simulations may also be parallelized by divvying up the order parameter over different processors. And in this example of a flat-histogram simulation of a Lennard-Jones fluid transitioning between a vapor and a liquid, the probability as a function of density is converging. Now, instead of having one processor computing this probability over the entire range of density as shown in this animation, independent processors could simulate separate density ranges that are later reconstructed to obtain the entire curve. However, efficiency is lost because the windows must overlap, and also because each processor may take very different times to converge. Now that I've introduced a few other parallel algorithms, let's discuss prefetching in a Monte Carlo simulation. Now, instead of attempting one trial perturbation at a time in serial, with prefetching we attempt multiple trials simultaneously. So for comparison, let's start with the serial example. Trial 1 is attempted from state A and is rejected, so we stay in state A. Then trial 2 from state A is accepted, and we move to state B. But with prefetching, a batch of different trials are all conducted simultaneously in parallel threads from state A. When threads are rejected, the state doesn't change, but when a thread is accepted, the state changes, and any remaining trials must be completely ignored. Thus, serial and prefetch Markov chains are identical, as shown in this example, where each prefetch thread now has synchronized into the same state B with changes due to rejecting trial 1 and accepting trial 2. The third trial must be ignored, and it is an example of wasted computational effort and inefficiency in the prefetching algorithm. This third trial is ignored because the second trial was accepted, so the third trial should have been attempted from state B rather than state A. Thus, prefetch efficiency decreases when trials are more likely to be accepted, and the efficiency also decreases when the overhead synchronization takes a long time in comparison to the first step of computing trial energy changes. The theoretical maximum efficiency of the prefetching algorithm is related to the probability of trial acceptance, where prefetching efficiency is limited by the number of ignored trials that are essentially wasted computational time. In practice, the efficiency may be lower than the theoretical limit due to synchronization time. Thus, the hope is that the second synchronization step is much faster than the first step, which is true if calculating the interactions of the particles is where the computer spends most of its time. And if each trial takes roughly the same amount of time to process, they won't have to waste computer time waiting for the other processors. The efficiency decreases with increasing acceptance probability because that leads to more ignored trials, such as the third trial shown in red. The efficiency also decreases with number of threads for the same reason, because the number of trials in a prefetch batch is greater with more threads, also leading to more ignored trials. Prefetching can be used at the same time as all of the other parallel algorithms I mentioned earlier, including configurational bias and order parameter decomposition. For example, a flat-histogram grand canonical Monte Carlo simulation to compute phase equilibria could be parallelized over 12 different order parameter ranges. Each one of these order parameter ranges could have 4 simultaneous prefetching attempts, and each of those could have 4 configurational bias threads. This means that the simulation is parallelized over 192 cores in total. Now, if the efficiency of each of these methods is about 75%, then together we can see a combined speedup of about 81 times. This means that a 3-month-long serial simulation could be completed in only 1 day using this parallelization approach. These are some of the methods I'm making available in my open source Monte Carlo software called Feast. And with this work, our hope is to make specialized academic research more accessible to businesses as part of the core mission of NIST. Now, for the remainder of the talk, I'm going to focus on the efficiency of prefetching alone, showing that 75% efficiency over 4 cores is both practical and achievable. Now, let's look at the efficiency of prefetching in a canonical ensemble simulation of a bulk Lennard-Jones fluid. In this type of simulation, the only trial move is a single particle displacement, where the maximum displacement is tuned to a given acceptance probability. From an algorithmic point of view, the density and temperature don't really matter, but we chose the same conditions as Mountain and Thermaleye used a few decades ago in their seminal work on optimal acceptance in Monte Carlo simulations. The cutoff was varied from 3 to 5 in order to study the effect of overhead. This is because the larger cutoff increases the time to compute energy, and thus decreases the relative overhead because interactions aren't computed during synchronization. The simulation was parallelized using OpenMP with Feast version 0.11, and efficiency was measured by computing the diffusion coefficient in real CPU time scale, not particle time scales. So the diffusion is computed with respect to the speed that the particle moves as observed by the simulator. Here I'm showing the diffusion coefficient and total CPU time as a function of the acceptance of a traditional single particle perturbation trial. The black line is the traditional serial simulation without prefetching, while the red line is prefetching with a single core, so you can already see a little bit of overhead that decreases the efficiency. The optimal serial efficiency around 20% acceptance was found a few decades ago, and this optimum is a result of a trade-off between making larger configurational changes with lower acceptance versus smaller configurational changes with higher acceptance. Now, when you consider prefetching with 2 or more processors, shown below, the optimum acceptance shifts to lower probabilities. This is because lower acceptance with larger configurational changes results in less ignored trials during prefetching. Note that the total CPU time in the diffusion coefficient includes a sum of the time spent by each processor. So the dashed line shows the theoretical prediction, not accounting for overhead, from the single core simulation, which can be used to accurately predict the optimal acceptance for a given number of cores. This means that if you want to optimize your parallel simulation, you only need to know the serial efficiency, and you don't need to evaluate the performance over many different numbers of processors. Finally, we can obtain overall efficiency by the ratio of the maximum diffusion coefficient to its serial value. Here, I am showing the efficiency as the ratio of parallel to serial diffusion coefficient. Each curve is for a different number of processors, and efficiency is shown as a function of the cutoff. Now, the cutoff is inversely related to the overhead. This is because a simulation with a larger cutoff spends more time computing energies and relatively less time on the synchronization overhead. The efficiency increases as the cutoff is increased and approaches the maximum theoretical efficiency shown on the right. Prefetching is more efficient for more expensive potentials, such as patchy particles or models with electrostatics, with the speed up of 3 times faster using 4 cores. Note that this was the efficiency target I mentioned in the earlier slides. Now the dashed lines show the reduced efficiency we would get if we did not optimize the acceptance probability and instead used the optimal serial value of 20%. As you can see, the reduction in efficiency is much more pronounced at larger numbers of processors. Now, everything I showed before was for the canonical ensemble simulations with only the standard single particle perturbation trials. But in the grand canonical ensemble, prefetching is even better. This is because there are also insertions and deletions. So in a dense fluid, these insertions and deletions typically have low acceptance. And if we look back at the theoretical maximum efficiency in prefetching that I showed before, remember that low acceptance trials with prefetching can improve efficiency over more processors. Thus, the prefetching efficiency in the grand canonical ensemble simulations is even higher than in the canonical ensemble. Here I'm showing the efficiency as measured by the time to converge a grand canonical flat-histogram simulation for various cutoffs, with a cutoff of 5 shown in black that has the lowest relative overhead. The error bars are a bit high compared to the diffusion coefficient measures I showed before, but you can still see that the efficiency is nearly double what I showed in the canonical ensemble. For example, in the canonical ensemble, 75% efficiency was obtained with 4 processors, but here in the grand canonical ensemble, the 4 processor efficiency is closer to 85%, or about 3.5 times speedup using 4 processors. So in summary, prefetching can speed up Monte Carlo simulations by a factor of 3 with 4 cores in the canonical ensemble, and in the grand canonical ensemble, efficiency is even better with a speedup of 3.5 times using 4 cores. Prefetching is implemented in the open source software called Feast that you can check out at this website, and many of the results I discussed in this presentation can also be found in this publication. In ongoing work, I'm also looking at load balancing trials that take different amounts of time to complete. For example, prefetching with a mixture of fast single particle trials and slower multi-particle trials, such as cluster moves. I'm also working toward enabling the use of prefetching simultaneously with both order parameter decomposition and parallel configurational bias. Finally, I'd like to end with mentioning that our group is interested in postdoctoral candidates for both the NRC fellowship and also collaborations with the pharmaceutical company. You can find more information at the website listed. Thank you very much for your time.